Well, hi there, boys and girls. Today we're going to take a look at how to find the volume of something that we create ourselves. And so what we're going to do is we're going to take a region or something that's bounded by maybe a function and an axis of revolution, and we're going to spin that region around an axis, and we're going to see if we can't come up with a solid, and we're going to find the volume of that 3D solid. And so this example right here has got f of x as this region, and I also have y equals 0, the x-axis, and x equals 0, the y-axis. And if we take this region and spin it around this axis right here, we would create a solid. And we're going to figure out how to find the volume of that solid. So here's the idea. First of all, we're going to take a little cross-section. We're just going to take a look at a really thin delta x, and we're going to spin that around the x-axis. And if we spin that around the x-axis, we're going to come up with some shape that looks like this little disc. Now, hopefully you can see that. If we spin that around the x-axis, that's what it would look like. Each one of these discs would be a little cylinder standing on its side. Now the volume of a cylinder is pi r squared h. So the volume of our disc would be pi times our radius is this distance off of the x-axis up to f of x. So we're just going to call that r of x, and then we're going to square that radius, and we're going to multiply it times the height. Now the height was the thickness of our cut, and that is delta x. That would be the volume of one disk. Now if we added the volumes of all of these disks together, you know, if we just did a whole bunch of these, we would get a summation, and we're going to have I go from 1 to however many rectangles we have. We'll say n rectangles, and then creating them, we're going to make disks of pi times all of these little r of x sub I squared delta x sub I, where we're going to let I be somewhere between a and b. So we're going to add up all of these little disks, and that would be the approximate volume of the solid. Now if we wanted the exact volume of the solid, we would need delta x to approach 0, which means we would need to get an infinite number of rectangles. So we're going to let the limit as n goes to infinity, I goes from 1 to n of pi times all of these r of x sub I squared times delta x sub I. Now we know when we did Riemann sums that there is a function that will do this for us, an infinite summation of a product. That's going to be our integral. And so this is going to be the formula that we are going to be using if we are going to revolve something around an axis of revolution. Pi integral from a to b of the radius squared dx. So let's take a look and let's just rewrite this for our formula. If we've got a volume around a horizontal line, or a horizontal axis of revolution, our volume is going to be pi times the integral from a to b of our radius squared dx. Now if we are going around a vertical axis of revolution and our representative rectangles are going to be horizontal, then we're going to have pi times the integral from c to d. These are going to be y values of our radius in terms of y squared dy. Now if for some reason that there is going to be a hole, if you're going to revolve the region around an axis of revolution and there's some space open, then we're going to have to subtract off that hole. It should make sense to us. It's called a washer method, and our volume is going to work out to be pi times the integral from a to b of our outside radius squared. That's going to be the full body, and then we're going to subtract off the inside radius, and this is just subtracting off the hole is all we're doing right there. And of course if we have a vertical axis of revolution, we're going to have horizontal rectangles. We're going to have pi times the integral from, I'll use c and d again, of the outside radius in terms of y squared minus the inside radius in terms of y squared dy. Alright, so hopefully I'm going to show you some of these tomorrow in class as well. And let's go take a look at some examples. So let's find the volume of the solid form. We're going to create this by revolving the region bounded by the graphs of the given equations about the indicated axis. So y equals 9 minus x squared is an upside down parabola. It's got a y-intercept of 9. It would have an x-intercept of 3. So I've got that upper region right there. Now x equals 0 is the y-axis. Sorry about not being straight there. I finally hit it. And then y equals 0 is the x-axis. And so we have a region right here. And we're going to take that region and we're going to spin it around the x-axis. So we're going to spin it around this axis right here. And we're going to come up with what that would look like. And we're going to find the volume. Take any cross-section right here. And we're going to find what that radius is. The radius is the distance of top minus bottom. Just always remember top minus bottom. How far is it from this graph down to y equals 0? And that's going to be your radius. And that is top function, which is 9 minus x squared, minus the bottom function. The bottom function is y equals 0. And I really don't need to write that, so the minus 0 part. So that is my radius. Once you find your radius, you're just going to do volume equals pi times the integral from, now we need our x's to range from 0 out to 3. We're going to let all of these rectangles range from 0 to 3 of your radius squared dx. That's our formula. Let's do one, and I'm not, you can do that on the calculator. I'm not going to type that in. Now let's do it about the line y equals -2. We'll see how that changes if our axis of revolution is not an axis, or like the x-axis. So there's my graph of 9 minus x squared. I'm still going from 0 to 3. I'm still bound by y equals 0 and x equals 0. So I still have this region. But this time my axis of revolution is going to be the line y equals -2. I'm going to take this region and I'm going to spin it around that axis of revolution. There is empty space here. We're going to actually have a hole in the middle. It's going to be like one of those things that you put a golf ball into. It's going to have a little hole here, a little ramp that goes up. And so what we need to do here is realize that we have some space, and we're going to have to use the washer method, which means we're going to have an outside radius and an inside radius. Now my outside radius is my distance from my furthest graph away all the way down to the axis of revolution, still using top minus bottom. So this distance is going to be 9 minus x squared minus -2. Top graph minus bottom graph. I'll just remember that. And so that's going to be 11 minus x squared. That is my outside radius. That would be, if there was no hole at all, that would be the volume of that solid. However, this is empty space in here, so I now have to find my inside radius, which is going to be the size of the hole. And that's from the closest graph to the axis of revolution down to your axis of revolution. And again, we're going to think top minus bottom. Now the top graph would be y equals 0, and the bottom graph is y equals -2. So 0 minus -2 is just 2. So that's the size of the hole, or the radius of our hole. So my volume is going to equal pi times the integral from, we're still letting all of these representative rectangles range from 0 to 3. And my formula is outside radius squared minus inside radius squared. We subtract this off because there's a hole in the solid. We had to subtract it off. And again, I'm not going to work that out. I'm going to let you do that. Alright, so now let's do it about the y-axis. So I'm going to have still my 9 minus x squared, but this time I'm going to spin this around a vertical axis of revolution, which means I've got horizontal rectangles. We always have to take our representative rectangles perpendicular to our axis of revolution, and this means we need to be working in y. So I have to solve 9 minus x squared equals y for x equals. So the first thing I'm going to do for y equals 9 minus x squared is I'll take the x squared to the other side and bring the y over, and then I'm going to take the square root, and when I do that I have to do plus or minus. So it's plus or minus the square root of 9 minus y. Now this is the positive version of that because these are all positive x's. So I'm going to have x equals the positive square root of 9 minus y. That is this graph in terms of x equals, or in terms of y. X equals f of y's. And I still have my y equals 0, and I still have my x equals 0, and I'm spinning it around the y-axis, and it's going to make this little dome-looking thing. So my volume is going to equal pi times the integral from, now this time I'm letting all of these rectangles range from 0 all the way up to this top point, which we knew earlier was 9. So that's going to be the integral from 0 to 9 of our radius squared dy. And of course, squaring that square root would just take it away, so you could just integrate from 0 to 9 minus y, and that would be the volume of that solid that we've created. It'd look like this cute little dome, what it would be. It'd be in 3D though, so we'd have this. I'm not very good at drawing those, but you get the idea. At least I hope you do. All right, now what about the line x equals -2? So this time we're still going to take 9 minus x squared, or since we're doing it around the vertical axis of revolution, the square root of 9 minus y, and we are going to spin that around the vertical line x equals -2. So we're taking this region and we're going to spin it around this axis. And again, we need to see that there's space in here. There's a hole between our region and our axis of revolution. And if there's ever empty space and we revolve this around that line, we're going to have a hole. We're going to have to subtract off a value. So we need to find what our outside radius is in terms of y and our inside radius in terms of y. And this time we're going to need to think right minus left. So my outside radius is the distance from the furthest graph to my axis of revolution. That distance is right minus left. That's going to be the square root of 9 minus y minus -2, which is really going to turn into a +2. My inside radius is my distance from my axis of revolution to the closest graph, and we still think right minus left. This graph is the line x equals 0 minus -2, and we'll make that a +2 as well. So my volume is going to be pi times the integral from 0 all the way to 9. We're going to let these rectangles go from 0 up to 9 of my outside radius, which is the square root of 9 minus y plus 2 squared, minus my inside radius, which is just 2 squared dy. Alright, let's take a look at another example. Sometimes we're going to take a region that's between two graphs and spin it around an axis of revolution. So I've got 2x minus x squared, and if you factor that, you factor out an x, you get x 2 minus x. So it's an upside down quadratic. We've got roots at 0 and roots at 2, and it's an upside down quadratic. My other line is just y equals x squared, or curve I mean. And so I can see my region. My region is right in here. That's bounded between those two curves. And I need to find out where they equal each other so I can let my x values range between x equals blah to x equals blah. So where does 2x minus x squared equal x squared? We want to get everything on one side, so 0 equals 2x squared minus 2x. And then we want to factor. So we're going to get x equals 0. Well, yeah, I can see that. And my other intersection is x equals 1. So it looks like that right here at 1, that's also where they intersect. Now we're going to spin this around the line y equals 3. Now y equals 3 is above this. Here is the axis of revolution, y equals 3. So we're going to take this region and we're going to spin it around this axis of revolution. Is there going to be a hole? Of course there is. There's empty space between my axis of revolution and my graphs. So we have to use the washer method. So I need to come up with an outside radius and an inside radius. My outside radius is the distance from my axis of revolution to the furthest graph away. And that distance again is top minus bottom. So that's going to be 3 minus the bottom graph here is x squared. The inside radius is the distance from my axis of revolution to the closest graph, which should be 3 minus 2x minus x squared. So finally, our volume is going to be pi times the integral between, we're going to let these x values go from 0 out to 1, of our outside radius squared, and then subtract off the inside radius squared dx. And you type that in on your calculator. So we'll practice this tomorrow, and I will see you guys then.